Yes, sir.
Yes, sir. Yes.
The full screen one, right? Not the
Yeah,
presenter
full
mode.
screen ones.
Full screen.
Yes.
Yes.
Okay, okay, thank you. So I have about an hour or so. Yeah, it's
Yes,
yeah.
sir. We have
Yes, sir.
an hour and we can have some questions.
Okay, perfect. So uh, yeah, thank you everyone. And I first of all, congratulate you for conducting this program on such a relevant topic. And I saw the speakers who had presented the previous days, and we have very good uh, sequence of talks. Very excited to see this happening. Uh, so I am going to talk about innovative materials and technologies to adapt to climate change. Actually, the title is very huge in scope. Uh, Climate change itself is a big thing, and then it's not all the materials and technologies that I'm going to talk about to adapt to the climate change. So I thought I'll first give a context of what I'm going to talk about. So first of all, I'm going to talk about the tropical region, and that is what is relevant for us. The kind of climatic conditions we see in most of the country. So it will mostly focus towards uh, reducing the heat ingress into the buildings and improving the cooling efficiency aspect of the buildings here. Then I'm going to talk mostly on the commercial and residential buildings. So I'm not talking about energy savings in industry or transportation or any other sector. It's focus only on the buildings. And again, my context would be building energy consumption and indoor thermal comfort, and that also during the operational phase of the building. So I'm not talking about the embodied energy. So it's quite limited in the sense that I'm talking only about the building energy and thermal comfort, indoor thermal comfort aspect, and how we can design and operate the buildings uh, to make them more resilient to the climate change. So this is the context I'm talking. I'm going to cover uh, several small and large strategies that can help us make the buildings and the environment within the city, as well as how we can adopt ourselves. I'll be talking about these aspects. So because there are too many things, I'll keep them brief, and I'll be basically giving an overview of what all can be done uh, in the buildings. So I have divided all these topics into three categories: passive strategies, active strategies, and it's not just the buildings which are to be changed or which are to be made resilient. Even we have to adapt ourselves, and I'll talk about that also. Okay. So maybe a little bit topics are a little bit jumbled here. Some of these fault detection and diagnostics will be coming in the active strategy. Okay, so I'll start with the passive strategies. Uh, I'll start with cool surfaces. So basically, cool surfaces can be on the roofs, can be on the walls, and can be on the pavements. And I'll talk about what is cool surfaces. And basically, they can help us in reducing the heat ingress into the building from the roof and the walls. They can help in reducing the urban heat island effect, and they can also help in reducing the impact of heat waves. So let us see what are the cool surfaces and how they help. So here I am explaining what's a cool roof. So cool roof is a roof which stays cool in the sun by reflecting sunlight. So basically, if you see in this picture, there is a dark roof and there's a cool roof. So the dark roof will reflect only 20% or 30% of the solar radiation that is falling on the roof. Remaining 70 to 80% will be absorbed, and then that heat will go inside and heat up the space. Not all the heat will go, but most of the heat will go inside. A cool roof basically reflects a large portion of the incoming solar radiation. So it will reflect about 80%, say, for example. So it will absorb only 20%. And out of that 20%, some will go inside the space. So cool roof stays cool because it reflects the solar radiation and reduces the absorption. And also it emits the thermal radiation. So whatever heat has been absorbed, it has to dissipate. As I mentioned, some of the heat will be going inside, some of the heat will be going out through radiation and through convection. Now, if the surface can radiate well, then it will be able to dissipate that heat more easily and it will remain cool. So whatever is being absorbed, that also should be dissipated easily to the outdoors. So that's the idea. So basically the cool roofs will be much cooler than the dark roofs. And there's nothing new about this. This has been known for maybe centuries. And this has been a traditional way of keeping our buildings cool, especially in the Rajasthan and Gujarat area of the country. So you will see simple things like lime wash or uh, China mosaic roofs in the traditional homes in the western part of the country. So technologically speaking, this is nothing new. This was known very well. But during the course of all these decades, with the availability of electricity and availability of AC, we probably lost this very simple technology because it is now possible to create comfort in the spaces with the use of ACs. So people forgot that they can coat their roofs white and save some energy. And that is the reason why we are talking about this cool roof again. And in the modern sense, it is available in many different ways. It is available as cool paints. It is available as tiles. It is available as membranes and even shingles. So from the technological principles, from the physics point of view, they are same. Maybe they have better efficiency than the regular whitewash or China mosaic tiles. These products may have better efficiency. They are visibly white, but they might have more reflection in the infrared region. As we know, the incoming solar radiation has two major components, the infrared and the visible. And a white surface might look white in the visible range, but it might not be that reflecting in the infrared range. So it is absorbing infrared, then again it will be not very effective. So if we have surfaces which absorb less of visible radiation and absorb less of infrared, that is they're reflecting both of them highly, then they are much more effective. And these modern materials are in that sense better. They reflect more of infrared also. Now you must be wondering that how this roof is cool. This doesn't look like white. It is uh, light brown and brown in color. So it is not necessary that the roof has to be only uh, white. Of course, white is better, but we can also get colored surfaces which are also cool. So here you see the spectral performance of standard brown and cool brown. This is the reflectance, and these are the wavelengths. And you can see that in the visible range, both of them reflect a very little amount of light. And therefore they appear brown. You can see here both of them look brown. However, when we get into the infrared, rather the near infrared region, we see that the standard brown doesn't reflect too much of infrared, but the cool brown reflects a lot of infrared. So a cool brown has an overall higher reflectance than a standard brown in the solar spectrum, And therefore, this can also be called as a cool product, a cool roof. So you can see that cool roof is available in several colors, and the colors match with the standard color. So visibly, we will think that these are regular colored roofs, but they are actually cool colors. Now the research is going beyond roofs. It is going for cool walls also, uh, because we are seeing a lot of multi-story buildings, and the area that is exposed on the envelope, if we see that area, then we'll see that the area of walls is much more than the area of roof, especially in the multi-story buildings. Uh, so will it make sense to put cool walls? So this is something that is being actively researched uh, at LBNL by Dr. Ronan Levinson, and they are trying to understand that if we have cool walls, what is the benefit? How much saving can be done? Especially because walls, not all the walls will get solar radiation at a given time, and unlike roof is getting the radiation throughout the day. Walls will not, because the sun will move from east to west, and also the buildings might get shaded from neighboring buildings. So all these things have to be considered. So one interesting thing is that walls have usually lesser insulation than the roof, and therefore the cool roof will be very effective even on, sorry, cool coatings would be very effective even on uh, walls. So, okay, so I have a question here in the chat. So somebody is asking, Sai Kumari is asking, but will it not heat the environment? Okay, that's a very important question. Uh, so generally it is perceived that this reflected radiation will heat the environment, and therefore it will be a not a useful thing at the local environment level. Okay, so let me explain. The incoming radiation is short wave radiation. Okay, and the atmosphere is mostly transparent to the short wave radiation. So this radiation can pass through the atmosphere and hit the roof. Now, a regular roof will absorb 80% and reflect 20%. So the 20% will go back into the space outside this atmosphere, but 80% is absorbed. Once this heat is absorbed, then it will be re-radiated, and that re-radiation will be in long wave. And the atmosphere is actually opaque to long wave, and that radiation will not go out from the atmosphere. So 80% of the heat falling onto the surface is actually heating the building and the neighborhood. In case of highly reflective surfaces, if 80% is getting reflected, then actually it is going outside the atmosphere. It will actually reduce the heating of the local environment. We will see that cool roofs can also help in reducing the urban heat island. So yes, most of this reflected radiation actually goes outside the atmosphere. And again, we did some studies here, and with the partnership from LBNL, we did some studies here, and we found through the measurements taken from satellite that this radiation actually goes outside the atmosphere. It actually goes out. So it is not just what we think, but it is being measured and shown that the reflected radiation goes outside the atmosphere. Okay, so the studies done at LBNL show that the cool walls can also be effective in keeping the buildings cool and reducing the energy consumption. So what are the benefits overall of cool walls and cool roofs? They increase the comfort in unconditioned buildings. They save the energy consumption in the air-conditioned buildings. The AC equipment can be downsized. That means, say, for example, if a building needs 100 tons, maybe we need 90 tons now because of the reduction in the load. And it actually offsets the CO2 and delays the global warming, because if we apply cool roof on a very large scale, and if we reflect the solar radiation back into the space, then it's as good as cooling the earth, right? So that much is the potential. It extends the roof life and reduces the roof maintenance. Now, whenever the roof undergoes a heating and cooling cycle, in winter, summer, or during the day, also when it's too hot in the day because of the solar radiation, and then it becomes cool in the night, there is expansion and contraction. And because of this, the cracks will develop on the roof. And if we have white roof, then these expansions are reduced because the roof doesn't get that heated up, and therefore it increases the life of the roof. And because the heat coming from the roof is reduced, we even need less insulation. So not only the cool roofs and cool walls help the buildings, but they also reduce the urban heat island, and they also reduce the heat wave. So we know that urban heat island is a phenomena in which the urban areas are warmer than the surrounding rural areas. And this difference can be 3, 4, 5 degrees centigrade. And this is not only in the daytime, but we can see this phenomena more also in the night time. So because of this extra heat, uh, there is more energy consumption in the cities, and also this brings a lot of discomfort to the people who don't have access to air conditioning. So there have been several studies which have shown that in the last 100 years or more, the cities are becoming warmer. And some simulation studies have shown that if we put cool roofs at a citywide scale, that is like, say, for example, if we say all the roofs in a city will be made cool, then the city temperature can be brought down. And this varies, of course, on how much area is covered by the roof and how much is the HI. But the impact can be really good. We can expect about 1 to 2 degrees reduction in the city temperature, and that is significant in reducing the energy consumption and improving the uh, thermal conditions in the city. There have been estimates that what is the benefit of cool roofs at a large scale, and Dr. Arthur Rosenfeld has estimated that 100 square meter of gray roof, when you convert this to white roof, that is as good as removing 10 tons of CO2. So whatever 10 tons of CO2 uh, has an effect on the global warming, that much can be offset by 100 meter square of white roof. And if we do it at a large scale, and if we do all the urban flat roofs in the tropics and temperate regions, then it will be as good as offsetting 24 gigatons of CO2. That's as good as saying that 300 million cars are gone for 20 years. That is the impact. So it's such a simple technology. All we have to do, we have to convert all our roofs from gray or black to white. And we will get the benefit as the building user. The city will get the benefit, and the benefit can be seen at the global level. Now, when it comes to heat wave, we see there is a huge benefit of having cool roofs. So heat waves is a period of excessive hot weather, and this is related to the usual weather that is there in the same area. So if these areas are hotter than what they are usually, then you can call it as a heat wave. Now, there have been studies which have found that uh, the death rates increase exponentially with the maximum temperature. And this maximum temperature is going to be higher in the cities because of the urban heat island impact. So cities will have much higher temperature, and then coupled with heat wave, this is a deadly combination. Uh, so here's a question. Are these special cool roof products available in India? Yes, these products are available. Uh, yes, mostly tiles and coatings are available. Uh, Generally, people are not using that much of membranes in India. The the another disadvantage of urban heat island effect is that this can be felt even in the night. The nighttime temperature is also very high, and it doesn't allow the at least the relief that is found in the rural areas in the night because of the cool temperature. So in cities, people are exposed to hot temperature throughout the day and throughout the night. And this is nothing new. This is the one of the early studies, of probably the first studies, and that is from 1972. So people have been studying the heat island and trying to see the impact of heat island on the deaths. And the projections are very poor. We are going to have several thousands of deaths if we continue to have uh, heat island as well as the the heat waves. So with the cool roofs, cool walls, as well as cool pavements, I have not covered the pavements here, but even our roads, which are very dark, if we make them a little gray, like cement roads, and uh, the city temperature can drop down, and all those uh, negative impacts can be reduced a lot. And there are several benefits of cool roofs, like cool roofs and cool pavements. I can continue. But here we are focusing on energy reduction, improving comfort and health, and lesser deaths during the heat wave times. Now let's move on. So we started with the envelope basically, and we started with the periphery. So we said, okay, we want to have first cool surfaces. Now what? Now we all know that if we add insulation to the envelope, the heat coming inside the building will reduce. So insulation is a good idea. And we also know if we have a lot of thermal mass, the the heat takes more time to enter into the building. And because of this, there is a delay in the heat to enter into the building. And this delay can help us offset the peak of the energy consumption, as well as if the delay is too long, then the outdoors are becoming cooler in the evening, and the heat flow might reverse the direction and start going out. So if you see when we talk about the traditional architecture and we talk about the palaces and havelis and forts, so they were very comfortable. They didn't have any electricity at that time, and they were still comfortable because they were thick walls, solid, big mass walls. And because of that mass, the the time lag between the peak indoors and the peak outdoors was several hours, and the heat would not enter into the space too much because the outdoors will be cooler in the night or late evening, and the heat will go back. So we want to have both the insulating effect as well as the thermal mass effect. But when we talk about the modern buildings, insulation we can still afford to put because it doesn't take too much space, but thermal mass is very difficult because there's no way a multi-story building can be constructed today with 1 meter thick wall, right? So we want to have as thin wall as possible, maybe 2 inches if possible, right? Uh, okay, so there's some messages which talk about what will happen if the roads are more reflective. So we are not talking of very highly reflective roads. We are just talking about, the regular black roads that we have with the reflectivity of maybe about 0.15 or so, and the cement roads that we have. So cement roads would have reflectivity of about 30%, right? Even this is good. So that makes a big difference. So a regular cement road in Indian context that we have, that we generally see in the highways, that is good enough. We are not talking of more reflective surfaces there. So it's not going to be 80% reflective. Okay. So, so how do we get the thermal mass effect in the modern buildings? And one of the possibilities is phase change material. So what is a phase change material? Any material which changes its phase from solid to liquid or liquid to gas is a phase change material. We have water, we can make ice out of it, and we can make steam out of it. So it's a phase change material. Now, if this phase change is happening at the temperatures that the building is normally witnessing, then it is good for us because during the phase change, a lot of heat is stored in the material in the form of latent heat. And therefore, we are not storing the heat as a sensible heat in the material, but as a latent heat. Therefore, it increases the capacity of the material for the same volume and the same weight. Meaning hereby that if I have a material, say for example, which solidifies at 20 degrees, okay? So in the night time when outdoors are pleasant, it becomes solid. In the afternoon, when the outdoor is 30 degrees, this material will convert from solid to liquid by absorbing the heat. And in that process, it will absorb a lot of heat because there is a phase change and it needs latent heat. So like this, the material which would have absorbed a limited amount of heat when it was not changing the phase can now store a lot of heat because it is now changing the phase. So we can put this material in the walls and give it a large thermal mass. But the question is that we should find out material which can change phase at the temperature swing that the building is witnessing. So in the night time, it solidifies, and in the daytime, it liquefies, and thus stores that heat. And then again in the night time, releases that heat. And we can design it in such a way that most of this heat is actually going out. So this heat doesn't enter into the space. So this is a relatively new area and not a very conventional construction yet, still more in research. Now, most of you are from the architectural background, and I'm sure you are talking about passive strategies. And I also see a lot of lectures that have talked about similar things. So I'll not get into details of the passive strategies. We all know that we want to have large uh, windows so that we can get daylight, we can get ventilation. But it's very important to have proper shading. If the windows are not properly shaded, then we can get more light than what is desired, and it can increase the cooling energy consumption. And it is not necessary to get daylight only from windows. We can get daylight from skylight. We can get different ways like light pipes and light shelves, and we can make it more efficient by getting more diffuse and more distributed daylight and daylight which penetrate deeper into the building. Lots of things can be done. Now, with the daylight, the advantage is that we can save on the electricity consumption uh, by dimming our lamps when sufficient daylight is available. And we can also, of course, open the windows and get natural ventilation. So we will see how can we make things active and get the maximum savings here. Now, one of the things that we can do is to improve our windows. Uh, Instead of a single pane normal glass, we can go for double pane or pane glass with gas filled in with lower efficient as well as low E coating so that the glass doesn't emit uh, the radiation inside, but it emits more to the outside. So like this, we can have very high performance windows and still get high transmittance so that we can get good view to the outdoors. Now, why just have simple windows? one possibility is, in the cities, when we are talking of tall buildings, the roof area is very small as compared to the facade area. And if you want to put photovoltaics and if you use only the roof, then the potential to generate energy is very less. So if you put photovoltaics on the facade also, then we can produce more energy. And if we put semi-transparent photovoltaic panels on the windows, then it's a win-win situation. We have more area, we can produce more uh, energy through the photovoltaics, and we are reducing the heat that is coming into the building. So maybe we might see soon commercially available windows which have inbuilt uh, semi-transparent photovoltaic panels, and that will help us in having high performance through the windows. Now let's see overall passive architecture, passive design, passive materials can help us in three ways. One, in unconditioned buildings, they can provide comfort. In conditioned buildings, they can help in saving energy. Now, a very interesting aspect that has come because of the climate change is increase in the power outages. So we now see power outages in cities which never had outages earlier, or they were very infrequent. Like in Mumbai, the power outages are not that frequent. Very rarely they have power outages, and because of uh, heavy rains and storms, now we see power outages in Mumbai. We see power outages in many other cities around the world, and that were not there usually. So, in case of power outage, the passive design can make the buildings more resilient, and people can still survive, and people can be a bit more comfortable than a regular building, which is not having any protection from the environment and only relies on the air conditioning or active devices to be comfortable indoors. So that's how the passive design can help. Now, let us talk about some active technologies. So let us continue with the facade. How about having dynamic facade? I think this would have been discussed extensively yesterday, so I'll not repeat. But what I will say is that a facade element, especially on the windows, if it can be dynamic, that is, it can close when there is solar radiation falling onto it, and or more heat is getting into the building than what is desirable. So it closes the window and reduces or blocks the solar radiation. That will be very helpful. It's not necessary that these have to be external. They can be internal blinds, internal curtains. They can be external, and they can also be in between the pane. So if you have double glazed window, then they can also be in between the two panes. Now this is a very simple thing, movable shades, but uh, new technologies bring very interesting aspects, and one of them is switchable or smart glass. So what is a switchable or a smart glass? So this is the glass which can change its transmittivity as per our requirements. So we can make it dark or we can make it light. So here I have a small video which explains this technology, and you can see how it looks like. Looks like the internet connection is a little bit unstable. Let me again play it at a high resolution because it wasn't very visible. Just a minute. Can increase the resolution right now. So here you see it is clear right now, and now it becomes dark. So this is dark here and clear on top. So it is possible to do this control at every panel. So panels are bright, more transparent, and it is also possible depending on where people are sitting, those panels get dark. So all this is very interesting. So we can control the amount of radiation that is coming from the glass and still have a very nice view. So view is not getting blocked. Just in case of blinds, the view gets blocked. So that will not happen. Now the problem is that if we want to control all these shading elements, then we need to measure what is the amount of light that is there in these spaces. And if there's glare or if there's too much light or too much heat coming in, then we have to control them. So to overcome that, to overcome putting sensors in space, uh, research is going on to see if we can use a sky-facing camera, and this sky-facing camera can take images of the sky and create a high dynamic range image of the sky, which can be used to model, to simulate the sky conditions as well as the conditions inside the space. And we can know how the light is getting distributed in the space, whether people are exposed to glare or it is glare free. And using all these calculations, we can control the blind. And here we are using a blind which is having different, so this is like a fabric which is having different porosity holes in that. So uh, this is like darker side or this is lighter side, and then we can bring the part of the fabric which has less number of holes if too much sunlight is falling onto the fabric to reduce the light getting into the space. So like this we can control the amount of light. So or we can have electrochromic window or we can have any other window there. So the question here is that can we, instead of measuring in each space, can we do simulations with the sky conditions known? Can we do simulations and find out how the space is illuminated and then control the lights as well as control the blinds? Not only this, we would like to control the window opening and closing also so that we can get natural ventilation. And if this can be automated, this can be wonderful because people generally don't operate their windows frequently. And once they close the windows and run the air conditioners, they don't know what's happening outside. And they don't know when the outdoors are pleasant and there's an opportunity to open the windows and switch off the air conditioning. So there can also be a simple advisory system, some kind of an alert which tells the users that outdoors is very pleasant, why don't you open the windows and save some energy. But it can also be automated. Now, if it is not done, then we can have forced ventilation. And even if it is done, we would require forced ventilation when the building is operated in the air conditioned mode. And during that time, we have an opportunity to recover some heat or recover some coolness here. So what is happening when we are having a space, we need fresh air. And we pull the fresh air from outdoors, put it into the space, and we have to remove the equivalent amount of stale air. Okay. Now this stale air and the fresh air has to be modulated depending on the requirement. So if we have more number of people, we need more fresh air. If we have less number of people, we need less fresh air. So here you see that CO2 sensor is put into the space, and when there are more number of people, more air is being brought in, and when there are less number of people, less air is being brought in. So what is the benefit of bringing less air? When we bring less outside air, we need less cooling because the outside air is hot and we have to cool it. And we can save on the air conditioning load by reducing the amount of fresh air that we are pulling in. So this is a very simple technique which can be very useful uh, for places which have highly variable occupancy. If the occupancy is fixed, then it doesn't help because all the time we are going to provide the same amount of fresh air. Now, when we are getting this outside air, actually these days it's not a good idea to call it fresh air. Outside air is the right term because outside air is also not fresh, right? So it can also be polluted. So when we are bringing this outside air, we have to have equivalent amount of inside air which has to be given out, exhaust air. Now the air that we are throwing out is actually cool because it is air conditioned room, so the air is cool, and the air that we are pulling from outside is hot. So there are heat recovery wheels which will transfer the heat from the hot air, which is coming from outside, to the cool air which is going out. And in that process, it will cool the outside air before it comes inside the space. So we can cool the outside air by the outgoing cool air and save some energy, right? So that is again a simple technology which can be used. And with the global warming and UHI and the city is getting warmer, the outside air is going to be warmer, and then we need more air conditioning to cool it, and therefore we can reduce that air conditioning consumption by cooling it, pre-cooling it using the outgoing cool air. Uh, let's talk a little bit about different appliances. We all know that the appliances are getting more and more efficient. These days we get fans which are very efficient. We get LED lights which are also becoming more and more efficient, and air conditioners also which are becoming efficient. And you might be aware of a global cooling price that is going on, and uh, which is a very ambitious price, which says that the price is to the to the team which makes AC, which is 5 times more efficient than the regular AC. And here by efficient, it means less climatic impact. Okay, so that's a fantastic target. And right now, this competition is going on, and the prototypes that are produced by these participants are being currently tested in the real life condition. So if we have such efficient ACs, it will help us reduce the energy consumption and help us reduce the climate impact. Okay. Now, not only we have to improve our air conditioning systems, but we can also have different kind of ways, different ways of air conditioning our buildings. So generally we have air conditioners where we cool the air, and then that cool air is circulated within the space. Now, instead of that, if we cool the slabs of the roof, sorry, of the ceiling or the floor, then we can transfer the heat radiantly, right? So the heat emitted from the body of a human being or from a computer or from any other device or light, it can be given to these surfaces like slabs or ceilings through radiant heat exchange. And why is it good? Because we are not moving all the air. We are able to save a lot of energy spent in fans, and we need not cool the whole volume of air. Here, the object which is hot is directly able to exchange the heat with the cooler surfaces, and therefore it saves energy. So that is another technique which is now gaining popularity, and now it is commercially used and used in regular offices. The problem with this technology, there are two major problems. One, we cannot cool the slabs too much. We cannot bring them lower than the dew point. Otherwise, water will start condensating on these surfaces. So that's going to be dangerous. And the second thing is that because we cannot do that, we cannot remove humidity from the space. We need another air conditioning system which dehumidifies the air. So in this type of system, we will have two air conditioning systems. The other system will be much smaller now because it is not cooling the space, but only dehumidifying the space. So the other system can be uh, basically just for dehumidification, a conventional air conditioning system, which can be much smaller in size. Now, so far we have been talking mostly about energy savings, but we have to look beyond energy savings. Uh, we have to see also about how the buildings can change their load in response to the availability on from the grid. So basically what's happening, the grid is not able to supply energy as per the requirements of the buildings all the time, because in the daytime the building requirement goes up and the generation is less. That can be the reason. Or if there's a lot of photovoltaics or uh, wind energy being supplied into the grid, then that supply is not uniform all throughout the day. In the night, say for example, photovoltaics will not be producing any energy, and therefore the grid will have less energy to supply. So basically, there is a difference in the demand and the supply, and there is something called demand response, in which the electric usage by the end users or the customers has to change from their normal usage in response to the price of the electricity or incentives given by the grid. So grid will say, okay, we don't have much electricity. Can you reduce your energy consumption? I'll give you this incentive. And the building reduces the energy consumption. So so we also see this in a way that when there is more demand than what the grid can supply, then we see blackouts, right? So some pockets of the city, they will switch off the electricity. Okay, and then we see the blackouts. So that is what is happening right now. But if all the buildings can participate in this system, and they reduce their energy consumption a little bit, then there is no need for blackout, because everybody will share the responsibility and reduce their energy consumption. So while a lot of things can be done, I am focusing more on the energy storage here. So what we can do, we can store energy when there is excess energy available in the grid, and we can use this energy when the grid has lesser energy available and the demand is more. So we can store this energy in batteries, electrical batteries. We can store this thermally. I'll talk about this thermal storage. And there's also a possibility of using um, electric cars, which are connected to the building as storage devices. So we store the energy when there's excess available, and when the energy cost is more, then we can extract this energy from the cars and from the building. Okay. So this is an interesting aspect that is emerging with the popularity of electric vehicles growing. And we can also have community level microgrids. So why I'm talking about these things, it is not just for demand response, but because of the climate change, there can be more outages. And during the outage, we can utilize this stored energy. So at a community level, if we have some photovoltaics which are generating, we have storage and we have the consumption. So this community can have much more resilience uh, to the climate change, especially during the outages, and they can have a better sustenance during the extreme events. Now let's talk about what is thermal storage. So instead of storing excess energy during off-peak time in batteries and using that electricity to run the air conditioners during the peak time, we can store the coolness in the form of ice. So why is it better? Because storing electricity into battery and then taking it out again and then converting into cooling through an air conditioner is little inefficient. And also we are using chemicals in the battery which have a life and then we have to throw them. And that causes environmental pollution. Here what we are doing during the off time, during the off peak time, suppose in the night right now, we assume that the electricity cost is low. We run the chiller and we make ice in a tank. Okay, so the whole night chiller is running and creating ice in the tank. In the daytime, when the electricity cost is high, we will not run the chiller, say for example, and we will run water in this tank and bring the coolness out and use a fan and a coil to cool the space. So like this, we can shift our load from daytime to the night time. We can save money because nighttime electricity is cheaper, and we can actually even reduce the size of the air conditioning system also. Like say for example, if I need 100 tons of the air conditioner for 8 hours in a day, now instead of that, I can actually go for 50 tons of air conditioner and run it for 16 hours in a day. And during the 8 hours when the building is not operational, I'll make ice. And during the time when the building is operational, I will use 50 tons of the AC and 50 tons of the ice and add it and use it together. So I can reduce my expenditure on the air conditioner. So it reduces my initial cost. It reduces my demand cost also because my total demand goes down. Uh, and in the end, I can save some money because I am charging the tank when the electricity cost is low. So it's a very interesting, simple system, and this is also now becoming, uh, mainstream because because in the daytime when there is a shortage of electricity, then sometimes there is blackout, and at that time we cannot run chillers on diesel generators, right? So we can still do cooling, but this time we can use the ice in the tank and discharge that ice and get the cooling. All we have to do is run a fan and a pump. No need to run the chiller. Okay. Now, when all these things are happening, it becomes quite complicated. This is just a pictorial view here, not necessarily in the same fashion. So we have some generation, we have some storage, we have buildings, we have other kind of end uses, and we have to control all this microgrid kind of a setup here and manage it. So this needs some kind of prediction and some kind of controls to manage this whole thing. So if I can have a system which can predict what will be the weather after 1 hour, how hot it will be, how cold it will be, how many people will be there in the building, and how much would be the energy required, what will be the cost of energy. If I get all this information, if I can predict this, then I can decide what to do and control the building accordingly so that the building is comfortable and we save money and keep the grid stable utilize the resources in the best possible way. So now I'll come to another topic. Here we were all talking about how do we adapt the buildings, but we also have to adapt. Uh, One of the things that we need to do is to use the adaptive thermal comfort to the best of our advantage. So what is adaptive thermal comfort? So adaptive thermal comfort is a principle that says that people experience differently and adapt to a certain extent to the variety of conditions, variety of clothing, and variety of physical conditions. So basically, I'll give a very simple example. We are living here in the tropical areas, so we are adapted to this. For us, 35 degrees, 38 degrees is not that uncomfortable. Somebody coming from cold areas, somebody, say, for example, coming from Northern Europe, will find 38 degrees to be too hot because that person is adapted to colder conditions, right? Similarly, if we go from here to colder regions like Northern Europe, even if it is summer for them, for us it is cold because the temperatures are around 20 degrees centigrade and we think it's too cold, and for them it's very good summer. It's pleasant. Again, because we are adapted to higher temperatures, and for us 20 degrees seems to be too cold. So the basic idea is that if we are living all the time in air conditioned spaces and we are running our air conditioners at 18 degrees or 20 degrees, we'll get adapted to that and we'll be uncomfortable at 25 degrees or 28 degrees, which otherwise would have been comfortable if we were actually staying in naturally ventilated buildings and getting exposed to those temperatures. Therefore, we should basically, first of all, not confine ourselves into these air conditioned boxes, which are maintaining low temperature and same temperature throughout the year. And we are getting accustomed to that. Therefore, we should keep ourselves more adaptive and keep ourselves exposed to uh, higher temperatures, which are still comfortable, which are not, I'm not saying go and expose ourselves to 40 degrees, within the comfort limit. And there are some standards which tell us that what are the comfort limits for human being, and if they are in air conditioned spaces and if they are in unconditioned spaces. So let us try to follow that and not have AC on all the time. Then we can also change our clothing. We should not be wearing, say, suit and tie in summers. It's really uh, not a good idea. It is too hot. We are running air conditioners, and then we wear jackets, we wear tie, and then we bring down the temperature to 18 degrees or 20 degrees. And then people who are not wearing the tie and the suit, who are actually environmentally more sensitive and they want to wear light clothes, they shiver because of the cold, and then they are forced to wear a sweater, right? So, so that's not a good idea, right? So let us wear the right clothing based on the season and based on the heating or cooling that's happening in the building, right? So generally we are talking about cooling, and therefore it's a good idea to wear comfortable clothes in summer when the cooling is going on, and do not reduce the AC set point too much, and then we can keep it high. Uh, and then, as I mentioned about the adaptive comfort, let us not keep the same set point throughout the season. So generally people set it at 25 degrees and keep it 25 degrees for the whole season. That's not a good idea. We can change it according to the outdoor conditions, and we can change the set point all the way up to 28 degrees and save a lot of energy. Okay. Now, when we talk about thermal comfort, so thermal comfort is individual oriented. Everybody has different requirements because of their metabolism, because of their clothing, and because they have different preferences. So if we keep the building at a constant uniform conditions, then it's not a good idea, because at the same condition, somebody might be feeling cold and somebody feeling hot. And so people are not comfortable, and probably we are wasting energy also. So if we can have personal environment control, here you see a cubicle. This cubicle has chilled water going inside it. So this can be cooled, and this coolness can be given to the user through radiant heat exchange. Just like we discussed the radiant cooling, here we are uh, uh, basically we are cooling the person through radiation, taking away the heat from the person into the panels and giving that heat to the chilled water and taking it out. So basically what it means that this small area can be cooled or heated as per the person's preferences. And similarly, lighting can also be personalized, and there can be a fan which can give again personal cooling, personal air movement. So all this interesting personal environment control can be developed, which can detect whether the person is there or not using the sensor, motion sensor. If the person is not there, it will switch off the cooling and the light. It can also detect the CO2 levels. If the CO2 levels are high, then it can change the fresh air supply. It can check what are the light levels. If light levels are low, it can provide higher light levels. So it can do all these things for the occupant. Now, how do we make a system which addresses all these things? So we provide comfort to the occupant. We save energy in the space. How do we save energy in the space? In the space, instead of running at 25 degrees, now I can run it at 28 degrees. So the whole office space can be at 28 degrees. People can reduce their localized temperature to 24, 25, 26, whatever, as per their requirement. The whole office lighting can now be at a lower level, say 200 lux, and people can use the task light to get higher levels of illumination, like 500 lux, for example. So like this, we can have ambient conditioning and task conditioning. So we can give comfort, we can save energy. And during the demand response event, when we want to reduce the load, we can bring the person in the loop. We can let the person decide what are the person's interests and what are the person's preference to different aspects of comfort. Like suppose right now I get a message that reduce my energy consumption, and I have a choice. I can reduce the lighting, I can reduce the number of monitors that I'm using, or I can reduce the air conditioning. So I can select what I want to sacrifice and reduce my consumption and still get the comfort and prioritize what I want. So here's this how this system works. So suppose there is a campus and there are some photovoltaic which are producing 600 kilowatt, and there's a diesel generator which can produce 1400 kilowatt, and there are 4 buildings, and right now the total consumption matches the total generation. Now suppose the total generation is 2000 kilowatt and the consumption is 2000 kilowatt, everything is going fine, but then there is a drop in the solar radiation, and instead of 600 kilowatt, now we are generating 400 kilowatt. That means we are short of 200 kilowatts. Then what do? We tell all the buildings to reduce their consumption. So from 400, building 1 has to reduce it to 360, building 2 has to reduce from 450 to 400. Like this, the building gets new target. Now, suppose this is our building 3, which has to reduce from 600 to 550, and it has 14 floors. The target is now given to each floor. So the target goes to each floor, and this is the floor level reduction that is required. Then each floor we need number of people, right? So suppose this is a floor and there are a lot of people sitting here. Then for everybody we give a new target. So everybody gets a target that, sorry, Yeah. So everybody gets a target, say for example, to reduce their energy consumption to 150 watts or 200 watts, something like that. Now let us look at this person. This is the radiantly cooled cubicle. The person has own light, a small fan, and the computer being used. Now this person gets the alert that you have to reduce your load. Now the person selects air conditioner to be switched off. That means this panel will not be cool now. So you see this becomes hotter and the fan speed increases to provide more comfort and the person is able to bring down the energy consumption in this cubicle, in this part, in this place, right? Uh, sorry. Now let us see other person. Now this person uh, is not happy and he reduces the plug load. So the charger connected to the computer gets disconnected and the load of the computer on the system reduces and he still gets cooling because he prefers to have more cooling and laptop is charged so not bothered about uh, the supply to the laptop. Now this is a power user. This person has lots of gadgets and doesn't want to compromise on thermal comfort also. So this person can say, I want to buy electricity. I want to buy some load. And another person sees an opportunity here and sells her quota of load to this person. And the trade happens. So this person instead of say 300 watts now has 100 watts. And this person instead of 300 watts limit gets 500 watts limit. So they are able to trade their quota and uh, overall the idea is that the whole building is able to reduce their load. Okay. Now, when we are operating buildings, there are always some faults that will happen, some small faults or large faults, and that will lead to wastage of energy. So, can we have a system which is intelligent and which can detect these faults and tell the building operator that this fault has happened and try to fix it? So there are different kind of faults, and not only that, these faults can be detected. Like say, for example, if the filter in the air conditioner is getting choked, or if the thermostat is not working properly, or the refrigerant has leaked from the air conditioner. It can be a simple fault, like somebody left the window open, right? So window is open, air conditioner is on, and we are wasting energy. So how can these be detected? How can we detect if a fault is going to happen in the future, and then we take appropriate action to fix the problem? Okay, and this can help in saving energy, getting better comfort, and avoiding a breakdown of the equipment. So a lot of interesting methods are there. I'm just giving you an idea that such kind of things are going to help us in operate our buildings efficiently and reduce the faults and save energy, even if the small amount of energy that is getting wasted because of some small fault in the devices. So one of the ways is that we can do real-time simulation and we can find out what is the expected performance of the building, what are the expected parameters in the building, and we can compare it with the actual parameters. And if there is a mismatch, we can find out, okay, then there is a problem, right? So like here, say for example, the blue one is the simulated load. According to this simulation, this should have been the load, but we are seeing a peak here. That means something is wrong. Then here, we see that blue one load goes down, the red one also goes down. But here we see the blue is going down, but the red is not going down. That means there is a fault here. Something is wrong that needs to be checked. So like this, we can also have energy simulation going in parallel to the real building operation, and we can do real-time comparison and you know uh, detect such faults and try to fix them. So That's all from me today on some of these technologies which will help us design and operate the buildings which are more climate resilient, especially from the point of view of tropical areas. So if you have any questions, we can discuss them now.
So any questions, you are free to ask.
Okay, there's one question. What are phase change material examples? There are lots of examples. I can probably send you a paper or two, which gives you various kind of materials that are available. So these are the materials which will change their phase at a higher temperature because we need them in the buildings and we would like them in this building operational temperature uh, phase change to happen at those temperatures. Okay. Is radiant cooling of ceiling suitable for warm and humid climate? Uh, yes and no. Uh, I can see you're talking about warm and humid. So humidity is a problem. And we have to be very careful that we do not bring down the temperature low. Otherwise, it will start raining in the space. So yes, it is possible. Actually, there is a building right in Chennai which is having radiant cooling and it works very well. But it has to be operated very carefully. And the humidity has to be removed through a regular conventional dehumidification system. Okay, so variable electricity billing is not in India as of now. Do you think this is on cards by Indian government? First of all, there is a differential tariff available in India. In Hyderabad itself, you have 1 rupee extra per unit in the morning and 1 rupee extra in the evening. It's something like 7 o'clock to 10 o'clock in the morning and 7 o'clock to 10 o'clock in the evening. The electricity tariff is higher by 1 rupee in the commercial. So ideally speaking, I will not like to run loads which are shiftable in these times. But with the smart meter, it is quite possible that we might have more variations in the cost of electricity, and we might even have real-time cost. So it can be varying every time of the day. And the cost will be communicated to the meters, and meters will communicate that information to the building, and there might be systems which can continuously control our loads so that we don't run unnecessary loads. Like say, for example, water pumping. I can pump the water in the night, in the morning, in the afternoon, anytime. Okay, and store it in the overhead tank. Now, if the cost of electricity is high from 7 o'clock to 10 o'clock in the morning, it won't make sense to run the pump at that time, right? So I will run it before 7 o'clock or I'll run it after 10 o'clock. So this is what we will be doing more frequently when the cost of electricity will have more variations throughout the day. Okay, so if you have any question, please feel free to write it here.
Sir, the cool roof efforts that you have been doing with the Telangana government, so cool roofs
Yes.
that you are working with the government of Telangana, like uh, would there be any policy, sir? Like because it is not only affecting the energies of the buildings, but also the urban heat island and then heat wave conditions. It's a very cumulative effect and cascading effect that it will be having. So does the government realize and are forming any policy on that, sir?
Yes, there is a draft policy which is already available and it is online for public comments. And the target is to get 100 square kilometer of roof area in Hyderabad in next 10 years.
Okay.
And this is the roof area, 100 square kilometer. And I think it is 400 square kilometer overall in Telangana. So that policy is still being formulated, open for public comments. And yeah, the idea is to get it up and running before the next summers so that we can
Sure.
start rolling out the program.
Like urban conglomerations like Hyderabad, if they can reduce their energy loads, there will be so much of energy that would be available for a lot of productive work.
Absolutely. And not only that, people who don't have access to electricity,
Yes,
urban
sir.
people, they
Yes.
don't have a fan, they don't have air conditioners.
Hmm.
They are suffering the maximum,
Yes, sir.
right?
Definitely.
Uh,
Heat wave conditions.
Hospitals,
Okay,
so,
hospitals. Yes, sir.
unconditioned hospitals, patients are suffering.
Yes,
So
sir.
the whole city is 3 or 4 degrees warmer,
Hmm.
then obviously it's a big problem.
Right.
So yes, with the large scale deployment, there is a possibility of reducing the city temperature. So let me see, there are lots of questions here. Adaptive thermal comfort and clothing is good, but in context to extreme climates, what are the solutions? Like in context to Dubai, where air conditioning is a basic requirement. Yes, I agree. Uh, some places are very, very hot and you have to run air conditioner, but there are two things that can be done. One, I am not sure, I don't think Dubai is hot throughout the year, right? So whenever it is not that hot, we should not run the air conditioning. Number two, when it is 50 degrees outside, we can run the air conditioner at 29 degrees or 30 degrees maybe and use a fan, right? So basically, let us not get acclimatized to 20 degrees. Try to keep our acclimatization to the highest possible temperature that we can comfortably bear, right? So wear clothing which is comfortable, keep the temperature to the maximum, use wind, use fans because they can give the cooling, the increase in the heat transfer. Therefore, the feeling of cooling will be there when the fan is there, and control the humidity. I think water is also a problem in Dubai, so I cannot say that use evaporative cooling there. But yes, keep the set point high and avoid air conditioning wherever the outdoors are pleasant. Okay. What are the smart mobile apps that can be used to monitor track our electricity, especially for old buildings? So this is very simple. I mean, nothing to do with the building age. We can always put a smart meter and get the live readings on the mobile app. We can also do something I wanted to cover, but I removed at the last moment because of the uh, you know availability of time. There's something called non-intrusive load monitoring. So there are some meters available which can detect what device is on at a given time. So if your AC is on, the meter will detect the AC is on. If your pump is on, it will detect. So not only it will tell the total energy consumption of the house, but it can tell how much AC consumed, how much pump consumed, major devices it can detect, and also tell you what time you are running it and how many hours you are running it. So it can give you a very good idea what's happening in your home. And this can be done in any building. Solar tube lights that fix on ceilings, whether it may lead to leakages in the roof. Yes, there is always a possibility. If the workmanship is not good, if the product is not good, it can lead to leakages. But it's as good as what you would expect in skylights also. So if skylight can also leak, this can also leak. So these are tubes which have a dome on the top, which will collect the sunlight, and the light keeps on reflecting in the tube because of the inner surface being very reflective. And then there is a diffuser in the end, which diffuses the light. And this is very much made in India now, locally available, and very, very effective, especially for the industrial buildings. Because in multi-story building, it is a problem. You can't make hole into your uh, flat, you know. But in commercial buildings where you own all the floors, you can bring it from the outside or through the floors, bring these tubes from the outside or on the envelope and bring it inside the room. You can bring it light. Okay. Can you please elaborate on thermal performance of building envelope? Uh, yeah, basically, we can give a value to this, a U value, we can call it. We can tell what is the overall resistance of the envelope. So we basically talk in various terms. We talk about conduction. So how much is the conduction from the envelope? How much resistance it is offering to the heat flow? That is one parameter. Another parameter can be air tightness. How tight is the envelope so that the infiltration doesn't happen? Then we can talk about the outside surface reflectance and the emissivity. So whatever heat is being absorbed, are we reducing the heat absorption and we emitting it easily? Then we can talk about the opaque surfaces, oh sorry, the transparent surfaces. We can talk about solar heat gain coefficient, how much heat is coming from the glass through the radiation and re-emission. We can talk about the visible transmittance of the glass, that how much visible light is coming from the glass. So these are some of the parameters that you will like to apply on your envelope. Okay, so it looks like there are no more questions and we are already at 11:30 also.
Sir,
So
like a automation, basically when I say home automation, it implies it is something to do with residential. But building automation, when we talk about commercial buildings and high value buildings, so definitely building automation, like the personal, the systems that you are talking about and all that. So building automation will definitely be a very positive impact on performance of the buildings, isn't it, sir? Then why is that not many buildings, all these uh, high worth buildings or high capital buildings, they don't go for a very small amount of capital for building automation, sir? Like, is there any challenges in building automation that we face now?
yes, there are several challenges. First of all, I see most of the large buildings would have building automation uh, to a reasonable extent. Uh, the challenges are, first of all, still this whole industry is not having good standards, or even if the standards are there, they are not following it. So the interoperability is less. So if I buy a system from a company A,
Mm.
I'm stuck with that company. I cannot change the components later on from company B. Okay.
Okay.
Like right now, I can always buy any light, any switch, any wire. It
Right.
works.
Mm.
I buy any player, any TV, any
Yes, sir. Yes, sir.
internet. They are not tied up with each other. They are all
Yes, sir.
compatible with
Independent.
other.
Yes, sir.
But that is not happening in building automation.
Okay.
So that is one problem. The second problem is the whole system is fragmented. You can buy a automation for lighting. You can buy automation for light, air conditioning. You can buy it for security. You can buy it for fire. You can buy it for elevators. They are all verticals. They are again fragmented. So it is not coming as a unified system. That is another problem. Cost is high, no doubt. Qualified people to run this are not available. See, we teach architects, we teach mechanical engineers. How many places you have seen programs which talk about building management, building operations, facility
Yes,
management, right? Very few.
very.
So it's important. They have to be technically qualified, not only how to operate, but they should also understand the design intent, how this was designed, how it is expected to operate, and then how do I operate. So those kind of expertise is not available. Then there is always a threat. If you have everything connected, there is always a threat of privacy. There is a
Yes.
threat of security, cyber attacks. So
Cyber
if
attack.
my building is too much automated, somebody remotely can switch off the building,
Mm.
right? Can attack on the building in that sense. So those are issues. Again, the standards and the importance that is required for this aspect is not there. So you would hear sometimes that hackers are able to switch on the cameras that
Mm.
people have installed at home. They are able to switch
Yes,
on
sir.
the speakers, smart speakers,
Yes, sir.
and they are able to. So if I can hack the smart speaker, I can switch on the light at your home,
Yes, sir.
right?
Mm.
Like there's nothing required. I can come outside somebody's home and say, Alexa, switch on the light. The light is on,
Yes.
right? So these are the problems that are to be addressed to make it safe, secure, and integrated, low cost, and interoperable. So all these things are yet to be solved.
Thank you, sir. Thank you.
Good. I don't see any more questions.
No, doesn't look like any other questions there. So yeah, thank you everyone. Really, it was interactive.
Yeah.
Lots of questions, and I thoroughly
Seema,
enjoyed
we
it.
had to take the picture.
Yes, sir, it's a tradition to take picture with all the attendees. So
Sir, if you can switch off your share screen, then we can take a picture of all the participants, sir, along with you.
Okay, okay.
Yes,
There
sir.
it
Thank you,
goes.
sir.
All of you, please turn on your videos for a quick picture.
So you'll take 2 pictures or 3 pictures? There are 3 screens. Right?
Three pictures, sir. It is mandatory, sir. We have to send it to FDP, sir, AICT.
Okay.
Yes, I think I'm done. Okay.
Thank you so much, sir, for such a beautiful presentation. Uh, Actually, you have compiled all the 4 days efforts, what we are looking at, climate change and adaptive architecture. You talked from elements like windows, glass, and till urban heat islands, encompassing the whole spectrum of the role of an architect in handling this climate change and the way we have powered adaptive architecture. So, thank you so much, sir.
Thank you, sir. Thank you very much for the
Thank
session.
you. Thank you for meeting me. Thank you. So should I log off now?
Yes, yes, sir. It's all right.
Thank you. Okay. We'll take a 10 minutes break. 11:45. All of you, please be back for the exam. It's an MCQ type of exam. It won't take more than 30 minutes. So after the exam, we'll continue with the valedictory function and we can close the FTP before lunch. Okay, so please take a quick break and come back by 11:45.
So the link will be provided in the chat box about the exam.
Yes. Yes.
Okay, fine.
Okay, thank
If
you.
you want an invigilated exam, we will have. We all can switch on
Sure.
your videos and we will invigilate.
We can play dual role also.
Okay, all right. We'll take a break and we'll come back. All right.